We will start by recalling some facts. Increasing-decreasing test. If the derivative of a function is positive on an interval, then the function is increasing on that interval. If the derivative of the function is negative on an interval, then the function is decreasing on that interval. Example: find where the function x cubed plus 1.5x to the power of 2 minus 6x minus 1 is increasing or decreasing. We did this one, so I'm just recalling everything. We differentiated the function. We have two critical numbers. We have to plot them on the real line. X equals -2 and x equals 1. And then we took sample points and we found out that the first derivative is positive between -infinity and -2. Then it is decreasing between -2 and 1. And then it is increasing between 1 to infinity. So we conclude that here the function is increasing, here it is decreasing, and here it is increasing again. Let's recall now the first derivative test. Let C be a critical number of a continuous function f. If the derivative of the function changes from positive to negative at x equals c, then the function has a local maximum at x equals c. If the first derivative changes from negative to positive at x equals c, then the function has a local minimum at x equals c. And if the derivative of the function does not change signs at x equals c, then there is neither a local maximum nor a local minimum at x equals c. We saw this example, and now let's see if you can observe at x equals -2, the first derivative changes from positive to negative, and we conclude that there is a local maximum at x equals -2. Here we have a change of the first derivative from negative to positive, and indeed we have a local minimum at x equals 1. There is also another test, a different one, to check for local maximum or minimum. It is the second derivative test. Let C be a critical number of a continuous, twice differentiable function f. If the second derivative is negative when x equals c, then the function has a local maximum at x equals c. If the second derivative when x equals c is positive, then the function has a local minimum at x equals c. If the second derivative at x equals c equals to 0, you cannot use the test. It's inconclusive and you have to use another test. The other test will be the first derivative test because there are only two tests to check for local minimum and maximum. Now we are going to use the second derivative test to find where the function fx, the one from before, has a local maximum or minimum. We already differentiated and we have the first derivative to be 3x to the power of 2 plus 3x minus 6. From here we have the critical numbers. Here is the first derivative of the function, and from here we know that the critical numbers are x equals -2 and x equals 1. Those are the x equals c that in the second derivative test, and we have to check each one of those. Now we have to compute the second derivative of the function. This is 6x plus 3. Now we need to apply the test. We are going to substitute -2 in the second derivative, and we get 6 times -2 plus 3, which is clearly a negative number. This is exactly the situation that tells us that there is a local maximum at x equals -2. This is this case. Now we will substitute x equals 1 at the second derivative, and we get 6 times 1 plus 3, which is clearly positive. And we can conclude that there is a local minimum at x equals 1 because of this condition. We already knew this from before. So here is what we concluded. I would like to recall that this was really easily done by the first derivative test, because actually when you analyze already the increasing-decreasing situation by analyzing the first derivative, you already can observe where is the local maximum and where is the local minimum. So this is just another way, which is not the better way, because you have to do the first derivative analysis in any case. Now we are going to use the second derivative test to find where the function f(x) equals x cubed has a local minimum or and maximum. And I would like to recall, if you remember, this function does not have neither local maximum nor minimum. But I want to show it using the second derivative test. If I will, not sure. Here is the first derivative. We need to do the first derivative to find the critical number. The critical number is x equals 0. The second derivative is 6 times x, and when we substitute x equals 0, we get 0. This is really bad news, because it means that you cannot tell using this test. It's very inconclusive in this case. So I have to use the first derivative test. Because the second derivative test may be inconclusive, and this is just another reason to prefer the first derivative test. I would like to recall that using the first derivative test, we can see immediately that there is neither local minimum nor maximum at x equals 0. Example: find the local minimum and or maximum of f(x) equals x to the 4. We are going to use the second derivative test, because I want to show you something. First, we need to find the critical numbers. So here is the first derivative, and the only critical number is x equals 0. The second derivative is 12 times x to the power of 2. Let's substitute x equals 0 in the second derivative. We get 0. And again, this is inconclusive and we cannot use the test. I'm going to use the first derivative test. If you do the first derivative test, which is pretty easy, if you look at the very simple first derivative being 4x cubed, we get that the function is decreasing and then increasing, and we conclude that it has a local minimum at x equals 0. I would like to recall that when the second derivative is 0 for some value of x, it's really inconclusive. It does not mean that there is no minimum or maximum. For example, in this case, when f(x) equals x to the 4, it was inconclusive, but there was a local minimum at the critical number x equals 0. The local minimum is f of 0, which is 0. Example: use the second derivative test to find where the local maximum minimum for the function f(x) equals 3e to the x minus 4x. Here is the first derivative. We have to find the critical number, so we want this to be 0. It is exponential equation. We have to solve that. 3e to the x equals 4. E to the x is 4 over 3. And x is ln of 4 over 3. There is only one critical number. Now we have to differentiate the function again to find the second derivative. It is 3e to the x. Now we need to substitute the critical number and find out what is the value of the second derivative when x equals ln of 4 over 3. It is 3 times e to the power of ln 4 over 3. E to the power of ln 4 over 3 is just 4 over 3, and we get 3 times 4 over 3, which is 4. It is a positive number, so we can conclude that f has a local minimum at x equals ln of 4 over 3. Example: find where the function fx equals e to the power of x to the power of 2 is increasing, decreasing, and where it has a local minimum and maximum. Check your local minimum and maximum by applying the second derivative test. Here's the first derivative of the function. Don't forget to use the chain rule. It's 2x times e to the x to the power of 2. To find the critical numbers, we want to equal this to 0, but I would like to recall that e to the power of something is never 0, it's always positive, so the only critical number is x equals 0. Let's do the analysis on the real line for the first derivative. It is 0 at 0, and this one is always positive, so it's pretty easy. When x is negative, we will get negative, and when x is positive, we will get positive. So the function is decreasing and then increasing. You can use the first derivative test, but you can also observe that you go down, then you go up. It means that there must be a local minimum at x equals 0. Now, I would like to apply the second derivative test to check my answer. The second derivative, we have to use the product rule here and the chain rule, and we get that. This is pretty messy, but we don't care because we just have to plug 0 for the x, and we get that all of that when x equals 0 is just 2. And 2 is a positive number, and we can get again that f has a local minimum at x equals 0. What is the local minimum? This is the y value of the function, so this is f of 0. F of 0 is e to the power of 0 to the power of 2, which is e to the power of 0, which equals to 1.